So we'll continue the lecture on hydration of alkenes. Hydration of alkynes. So the primary idea of hydration is you're adding a hydrogen and an OH group. So remember the topic that this is an acid catalyzed hydration. So in acid catalyzed hydration, we are having Markovnikov addition. So the more substituted carbon gets the OH, the less substituted carbon gets the hydrogen. So the mechanism is, if you consider this to be a generic alkane, so you have the presence of an acid with water and mercuric sulfate. So this mercuric sulfate is required because the reaction is slow and it increases the rate of reaction. So what happens here in this mechanism? So if you take a simple alkyne and react it with H2SO4, H2O and HgSO4, the product that you get is, notice that the red represents the more substituted alkyne, the carbon, and the blue represents the less substituted alkyne. So this is more substituted. So the red one gets OH. So you lose the 2 electrons. These 2 electrons then bond with the hydrogen. So you end up with this structure. So this structure is called an enol. So it's a combination of an alkene and alcohol. So enols are generally not stable. So the final product that you end up with is it loses the proton. So that results in a stabilized double bond structure of a ketone. So for example, let's say if I take a simple alkyne right, with H2SO4 and H2O. So if you consider this compound, so the product that you get initially is you have 2 carbons. So you have this carbon in blue and carbon in red. So the carbon in red is the less substituted carbon. The carbon in blue is the more substituted carbon. So the more substituted gets OH, the less substituted gets H. So you get OH. And on the less substituted, you have a hydrogen addition. So this is the enol that forms. This enol, under further reaction in presence of the acid, and H3O plus, it loses the proton to H3O plus, resulting in a double bond on the OH group and a single bond. So this is a ketone. So one way to remember this is the more substituted carbon gets a double bond oxygen, the less substituted carbon gets the hydrogen. So this is the way to remember the structure. And this is the hydration of alkynes. So next, we'll continue the discussion on hydroboration and oxidation of alkynes. So hydroboration and oxidation also involves the addition of hydrogen and OH groups, but the trick here is it undergoes anti-Markovnikov addition. So the compound that you get here is also an enol, but the enol then undergoes a change in structure and forms an aldehyde. So now if you take the general structure of hydroboration, so hydroboration is regioselective, so it's also anti-Markovnikov. So it also produces enol that then tautomerizes to form aldehyde. So the process of tautomerization is the rearrangement of protons. So proton that was originally here will go down there and become hydrogen. So this tautomerization is base catalyzed, it's not acid catalyzed. So in this reaction, if you take a general alkene, let's take a general alkyne. So you have two carbons again. One is a more substituted carbon, the other is a less substituted carbon. So because it's anti-Markovnikov, so you end up with OH on the more substituted one and OH on the less substituted one. So the reaction will continue as follows. And the compound that you need here is hydroboration, is BH3 and THF. And you need a base, so you get a hydrogen peroxide and NaOH. So that then results in the structure forming a bond, double bond with OH and a H. Because double bond with an OH is unstable, so OH generally gains a positive charge. So this then results in an enol formation. So now the enol loses the proton to OH minus, so OH minus, and results in the formation of the proton will basically move its position, so resulting in an R bond, double bond O and H. So this is a general structure of a aldehyde. So this is the common reaction of hydroboration and oxidation. So let's take a simple example. Let's say this is a simple alkyne. So you have two carbons. So this is more substituted, this is less substituted. So the more substituted one gets hydrogen, the less substituted one gets OH. So in anti-Markovnikov addition, the reagents that you use are boron trihydride, tetrahydrofuran, hydrogen peroxide, and NaOH. So in the initial reaction, you end up with a structure where you get hydrogen on this side and a double bond with an OH group. So this is a structure of enol. This structure then stabilizes, so it undergoes resonance stabilization. So this then results in the formation of hydrogen on this one and a double bond O. So this is a structure of an aldehyde. And this is the final structure that you end up in the structure with. So this is the full reaction for any structure. So pause the video right here and try this problem. Products of BH3, THF, H2O2, NaOH. So try this reaction and see if you can find the product, the final product. So write the enol and also the aldehyde form. So let's continue the reaction. So how do you control the hydrogen reselectivity? So for a terminal alkyne, the Markovnikov hydration yields a ketone, and anti-Markovnikov hydration leads an aldehyde. So if you have a terminal alkyne, if you combine it with H2SO4 and H2 with mercuric sulfate, you get up a methyl ketone, and if you combine it in presence of a BH3THF and H2O10NOH, you will get an aldehyde. So hydroboration and oxidation. Hydroboration and oxidation leads to an aldehyde formation for a terminal alkyne. And acid catalyzed hydration leads to a methyl ketone, a general ketone in its structure. So in the next topic, so let's talk about halogenation. So halogenation of alkynes yields a tetrahalide. So tetrahalide reacts in common sense. When you think about the reaction, if you take a simple alkyne, so if it undergoes a reaction with excess X2, halogenation occurs in the presence of carbon tetrachloride, CCl4. So the X can only be either chlorine or bromine. So the reaction leads to the addition of two carbons. So with the double bond, so the two carbons that have the triple bond end up getting two X2 halogens each. So you end up with a structure R, C, X, X, C, X, X, R. So this is a tetrahalide. So this is the formation of halogenation. This is the process of halogenation of alkynes. So pause the video right here and try the problem and guess what would be the product. So halogenation can also have regioselectivity in terms of both anti and syn addition. So each equivalent of halogen results in anti-addition as a major product and syn addition as a minor product. This general process is generally not understood why it happens that way. So what we know is that anti-product would be obtained in more quantities. So the next topic is ozonolysis. So if you remember, we talked about ozonolysis in the last topic as well, when we talked about oxidative cleavage in alkenes. So now let's talk about ozonolysis in alkynes. Alkynes do the same thing exactly, but rather than having them split across the structure, they generally form carboxylic acids. Rather than splitting them and forming ketones, they form carboxylic acid. So let's take an example. So if you consider the following structure. Consider the following structure. Ozonolysis happens in presence of oxygen, ozone, and H2O. So first it reacts with ozone, and second it reacts with H2O. So the reaction splits the triple bond and forms two products. So they look somewhat like this. So you have the two carbons. So this is one of the carbons and this is one of the carbons. So split it across the carbon structure. So you get a double bond O and NOH plus and this structure where you have a double bond O and an OH. So this would be the splitting across the structure. So the difference is each split results in an oxygen double bonded and a bond of OH, an oxygen double bonded and a bond of OH. So this structure of bond C double bond O OH is called as a carboxylic acid. So when you split the ozonolysis of alkynes results in carboxylic acids. Specifically, the result of 2 carboxylic acids. So now take the following reaction and let them undergo ozonolysis and try to find the products, the 2 products. So take a pause here and try to see if you can work out this reaction. So I also have another example in the slide. So use this and see if you can work out the product of the ozonolysis reaction here. So in the next part, let's discuss alkylation of terminal alkynes. So we talked about terminal alkynes. So terminal alkynes, they lose proton and form alkanide ions. So we also said that the alkanide ions are generally good nucleophiles because of the excess amount of electrons present. So because of their good nucleophilicity, they undergo SN2 reactions with alkyl halides. So this results in a new bond formation in place of the hydrogen. So they undergo substitution reaction. They substitute hydrogen for a halogen. So let's take a simple example. So in a general structure, if you take R bond C, triple bond C, bond H. So the proton goes out, so results in the electron. So the proton leaves the electrons to carbon and goes out. So this results in the formation of alkylate ion. So this is an alkanide ion. So this alkanide ion is generally a good nucleophile. So if you mix an alkanide ion if you have HX, the X attaches itself to the carbon, resulting in R bond C, triple bond C dash R. So this structure is the process of SN2 reaction. So remember that R here is the one that attaches itself and not the X. R is the one that attaches itself to the carbon, not X. So X leaves, so it takes its electrons and it leaves. So R bonds with the carbon to form this process is called alkylation. This process is called alkylation, and this only happens in terminal alkynes. So terminal alkynes are where the triple bond is on the end of the parent chain. So let's take a simple example. So let's say if this undergoes a reaction with CH3 EX. So let's calculate terminal alkyne. So this is the reaction. So EX here, let's consider EX to be some substance, let's say Br. Br takes its electrons and goes out. The CH3 becomes CH3 plus, and the charge here, the compound loses its hydrogen, so this then attaches itself to the carbon. So with the final product being a double bonded structure, so it's a triple bonded structure with CH3 on one side. So this would be, so you get from a terminal alkyne into an internal alkyne. So you start as a terminal alkyne and you end up with an internal alkyne. So take a second and write down the structure what you would get for the product. So find the product of this reaction. So alkylation is not that good of a reaction with SN2. Does not work really good with secondary and tertiary halides. So it only works with methyl and primary halides. So E2 dominates the secondary and tertiary halides. So if you consider this to be a terminal alkyne, so in presence of NaNH2, and if you consider the halogen here, this bonds here to form a new triple bond C. Acetylene can undergo two successive alkylations because of the presence of two hydrogens. So both hydrogens can undergo alkylation to form an internal alkyne. Or you could call it a di-substituted acetylene. So this is an example of alkylation of terminal carbynes, alkynes. So now let's talk about synthesis strategies. So recall the common methods that we talked about, where you convert a triple to a double or to a single. If you want to convert completely from an alkyne to an alkene, we use a catalytic hydrogenation. But if you want to convert an alkyne into an alkene, you do the reaction in the presence of a Poisson catalyst. So where it stops the reaction from further continuing from an alkane to an alkyne. So when you want to convert an alkene to an alkyne, it undergoes the same catalytic hydrogenation. So what if you want to reverse the process or decrease the saturation? So this process requires synthesis strategies. So halogenation of an alkane is then followed by elimination, and that yields an alkyne. So this alkene, if you undergo halogenation, it forms a dihalogen, dihalide, that then under excess sodium amide results in an alkyne. In the same way, you can do the entire reaction the same way here. You can convert an alkyne into an alkene using a Lindlar catalyst, and then from them you can use catalytic hydrogenation to form an alkene. And then again, if you want to convert an alkene into an alkyne, we use halogenation followed by elimination. So that results in the formation of an alkyne. So this interchangeability is what is required to understand all the reactions. So this is a summary of all the reactions. So you can go through all the following reactions, and I have put an entire synthesis table. So this is the summary. So each number has its own reaction here. So as a given, make sure that you go through the entire structures and how the transformation is taking place, and make sure you practice at least one reaction. You can find multiple of them at the end of each topic in the textbook. So practice at least one reaction for each of them so that you understand how the reactions generally work. If you remember the reagent, you can remember the process. So that ends this chapter.